Uh, yeah, and I think the background uh, for this is that long time ago I was many years working with MySQL and MariaDB, and of course we have a lot of different databases in this conference, but maybe the background of many attendees is the same as mine, and in that sense, it was nice to be re-invited back by Federico. That's where we know each other as well from the MySQL and MariaDB community. And so so for the talk, I will talk about various ideas I've learned from other databases that I think are interesting and not so well known, and that might be interesting to attendees of this conference. But I actually have some news also. So in this context, it's a coincidence that tomorrow I will start a new gig at Ivan, the Finnish database as a service company, and specifically I will start on their MySQL team. So from tomorrow I will I will maintain MySQL servers in production and do backups and automation and stuff. So that's quite exciting after all these years. Mostly, also it's a return to SQL from NoSQL. So, uh, but that's not. That was just like a coincidence that it happens the same week. So I wanted to share. Uh, Also, if somebody is interested in what I've been doing the past 2 years, I did not work for a database company. Rather, with Matt Fleming, we started a company called Nyrkio that does tooling for performance testing. So essentially, we are trying to mainstream and make easy to use tools and methods that we used in our own careers over the past 15 years almost. And the first product that you see here is the change detection, which has been quite successful. This was first developed when I worked on the MongoDB performance team, and there is an open source project, Apache Ottawa, that this is then like a web front end for. And another interesting product that we are now piloting with the Turso database, another Helsinki database company, by the way. We are piloting test runners for GitHub. So you can use what is called self-hosted runners or third-party runners for your GitHub workflows, and the initial results are quite interesting. If you look at this picture here, it's like just from yesterday or so that there are two consecutive test runs. The thing, I guess it's almost invisible in this slide. So the cool thing in this picture is that these 2 points are actually within 1 nanosecond of each other. Yeah, we will offer servers which are tuned for maximum repeatable test results, so that you have low noise, and therefore if you have actual performance regressions in your code, that will be easy to catch. So just something I'm working on. So now for the topics today, there is actually something linking them together, but mostly this is 3 different topics I thought might be interesting to talk about, and the first one is code transactions in Cassandra. I think they are now finally this year in the latest release. They are GA, and you can use them in Cassandra. I worked on this already 4 years ago, 5 years ago when I started. Almost immediately when I started at DataStax, this was a topic. So to explain the context, like why Cassandra users wanted this and like what it adds to Cassandra. First, we should understand what kind of database Cassandra was without distributed transactions, and what are the typical use cases. So Cassandra very much is an implementation. Actually, I would say it's the most popular implementation of the famous Dynamo paper that Amazon employees published in 2007, which was like a solution to the problem presented by the CAP theorem paper, and it's worth pointing out that even like when you use the DynamoDB from Amazon, I don't think if it ever used this architecture, or at least not as long as I can remember. DynamoDB itself hasn't used this, but Cassandra kind of made this a success, and where this works well is Cassandra's architecture and this Dynamo architecture is optimized for write availability. So you can choose consistency levels where your write succeeds always, but you don't necessarily have consistent reads if there is some node failures or network partitions. To some extent also Cassandra, and I think this actually reminds me of early MySQL in some ways. So Cassandra also had some solutions that were very kind of simple and pragmatic. One is that they just used the normal clock timestamps as transaction IDs. Of course, like milliseconds or microseconds granularity or something. But even so, if your server clock was not set correctly, then you could get into a lot of trouble. So it's kind of shaky architecture, but sometimes simple solutions become popular, and the other databases that implemented Dynamo, like Riak and so on, are no longer with us because they were too complex to understand, even though in theory they were much better than Cassandra. So then over the past decade or so, like let's say from 2012 to 2022, there was a understanding of these high availability issues and consistency improved, and so instead of the CAP theorem, people started understanding that there is actually quite a granular topology of different consistency levels and or lack of consistency, which we call anomalies, and then ultimately there have been proposals also for implementing something that would be the strict serializable level, which actually most databases never implement. And so FaunaDB is maybe the most well-known that tried to implement this, but I haven't heard much from them in recent years either. So the interesting conclusion here is, which we know from MySQL and Postgres worlds as well, that even if a database supports serializable, for example, doesn't mean that users actually want to use that. But in some more academic circles, people think it's it's something that databases should support and provide. So and if we go back to the CAP theorem also, the more granular understanding that developed, let's say 20 years after the CAP theorem was first published, was that it's not so black and white that you either have consistency or you have availability. So in reality, whichever architecture you choose, no system will be 100% available. Like sooner or later you will have downtime because there is some failure that you don't survive. And then if we think about it the other way, like you see here, also these consistency levels, it's not like something is consistent or not. Often with like relational databases also, people ask like, is your database ACID compliant? So it's not like a thing you are. Even if you support the SQL standard, there are like four different levels. So if you support read uncommitted, is that ACID compliant, or does it mean that you have to be strict serializable? So it doesn't, like just saying CAP theorem or ACID doesn't actually mean anything. You have to be more specific. And so with this background, there was a proposal in the Cassandra project to implement a new distributed consensus algorithm, which they call Accord. And this was around the time that I had started there also. And I liked the white paper and like the proposal of the algorithm, so I defended it also. But my contributions mostly to this project were to eat sushi in London with the Apple developers, and then eventually in Palo Alto. So it was like a act of diplomacy between DataStax and Apple engineering teams, which I suppose that part I was quite successful in, to get everybody to work together. So what they proposed was to do a strict serializable, because why settle for less? And they actually copied some ideas from Calvin there. And then also why they needed to implement their own algorithm to a large extent had to do with trying to create something that would be kind of aligned with how Cassandra is already used in production. So typical Cassandra deployments, at least the large ones at Netflix and Apple and these kind of companies, often stretch across multiple continents, and you also have writes in all the continents. So Cassandra, or the Dynamo architecture, supports what we used to call multi-master when I worked with MySQL and Galera. So they wanted to develop a new algorithm that would be compatible with the user expectations there. So I will talk about this now a little bit, and on the previous slide you had a link directly to the proposal and the white paper that describes it. Now, of course, there is also when it's GA, there is like end user documentation and several presentations, and here is also a link to my own blog where it was kind of done for myself. I was working on a few bugs at the end of before I then left the DataStax, but this is like a easy to read version of the algorithm description, and that I wrote on my blog, because I get kind of dizzy with these Greek letters that academic articles use. So the one thing that nobody in the Accord team actually realized this, but in my opinion, the high level flow is actually similar to Galera, where transaction transaction from the replication point of view becomes a write set, or could be a read-only set in this case, because you also because you support strict serializable, so you may want your reads to be transactional also. But yeah, a write set of the keys that you modify is sent around, and the first thing you do is that you figure out total ordering between these transactions. Of course, you have to take into account then the keys that are modified, so that the ordering makes sense, and there isn't like circular dependencies or such things. And once you figure out this ordering, then actually the execution of the transaction, or applying the transaction to the database, happens independently on each node, and it's kind of a done deal at that point. Of course, from a performance point of view, applying the transaction might still be a lot of work, but there is no question that it shouldn't succeed. So it's guaranteed to succeed at that point. And then these things that are not in Galera. So the first thing, of course, is that this is across shards. So essentially, if somebody in MariaDB or MySQL wanted to implement a sharded cluster and build it on the Galera protocol, then something like this might be interesting. And that's like the additional thing that Accord does, that it's not in Galera. And we have, and then the strict serializable is the other thing. Galera, if I remember, was implemented as snapshot isolation, and here the biggest difference is the same, that like if you want to support serializable and strict serializable, it means you just have to include all the reads in the transaction as well, not just the write, and that of course can be heavy, because like you probably shouldn't, with this kind of system, read thousands of records. It gets quite heavy when essentially your reads are just as expensive as writes if you do this. So you have to consider that in your transactions. And the other thing that comes from Calvin is that you can have like arbitrarily complex transactions in some sense. They can be as many shards as you want, as many rows as you want, as many statements as you want. So there is a example on the next slide. We can just as well go there. But a key innovation that came from Abadi's research team from Calvin is that the transaction is a single shot transaction. So you have to write all these statements, and you can define variables and use them in later statements, but you don't have this kind of interactive session where you can do a select statement and return data to your code or to your shell even, and then continue doing things, and then in the end you do commit. So you have to do like everything in one shot, and the way they achieve this strict serializability essentially is that actually it's in a way single threaded. It is literally like serialized when they apply the transactions on each shard, and that's why you have to send all of it together. Yeah, I'm not gonna spend more time on that syntax, but I just wanted to show. And of course, like because it's single shot, so the way it works is that you do all the selects at first, and then you do all the writes together. That's also like dictated by the algorithm. So a couple of interesting optimizations that then are in a code. So what I described now is like the basic structure, and then there are two things that I thought were cool. In fact, they also like added flexible paxos, which Heidi Howard published some years ago. And the idea with flexible paxos is that you can get better performance in a geographically distributed cluster if you are willing to trade fault tolerance. So what you typically do here, we have 9 nodes. So you agree that actually, in a way, the relevant nodes could be just 5, and the others are essentially followers. And now between these 5 nodes, which are called an electorate, then from those you need to have a majority quorum. So that means 3 nodes out of 5 is sufficient to commit a transaction. So with this trick, we have defined the 3 nodes to be like a majority or quorum. But this means in this setup, you can only tolerate like one node failing. So of course those 4 followers that are outside the electorate can fail at any time, and they are kind of ignored for this purpose. And what happens, and like why is this a big deal, is if you have these nodes distributed far away from each other, the difference in using this can be that you have 3 nodes in the local data center, and that's sufficient to commit transactions. So you might have like, a few milliseconds latency instead of hundreds. And this was one of the key things that like design goals in having efficient writes in Cassandra, where like this behavior is similar to what users expect from existing applications. The other thing I think nobody had realized, and what they realized when building a code, was that it isn't really a trade-off anyway, because you can at any time like change this configuration to go back to like 9 nodes or 6, 7 nodes or 5 nodes. I guess it's always odd number, but anyway. So now if it happens that one node fails, then you just immediately reconfigure to a slightly larger electorate, and then you can again tolerate a second node failing. So essentially, like there is no real trade-off for using this optimization, but nobody had realized it before 2022 or 21. The other thing that was cool is the reorder buffer. Actually, this was very confusing for everybody that read the algorithm, because it was written in a way that made you think of spanner, and that that this was somehow very important. And then only when the developers said that no, this is actually like completely optional performance optimization, then I understood this correctly. And so the idea here is a code still uses timestamps as part of the transaction ID. But the timestamp alone doesn't like automatically become the transaction ID, but it's like a seed for it. And now when the nodes have to order transactions with each other, of course, if you have, like on the left side, you have the client for transaction 1 or transaction coordinator for transaction 1 is close to this. Let's say this is like a Western data center on the left side. So transaction 1 arrives first on that node, and then hundreds of milliseconds later, transaction 2. So that means what the node would do, it would it would look at the write set in transaction 2 and say that, oh, like I've already approved some transactions here that are conflicting. So unfortunately, like I cannot approve transaction 2, but so what then would happen is that you have like a second round trip where you have to renegotiate the transaction ID. So the transaction doesn't fail. These transactions never fail as such, but what happens is that there is a performance penalty when you have to recalculate the transaction ID. So then of course the same happens the other way. Also, when transaction 1 has to write some shard that is controlled by the node on the right side in the east. So then essentially when you have many concurrent transactions, then they might all fail because of some other, like not fail but not be able to use the what they call the fast path. And for this reason, what they do is that transactions actually choose a timestamp that is some amount of time, like some, let's say hundreds of milliseconds maybe in the future, with the idea that the transactions can then travel to all the nodes anywhere in the world, and still their kind of official arrival time is in the future. So then all the nodes will physically have the transactions, but they will keep them buffered until the transaction ID like actually happens, and then this way they kind of arrive at equal times regardless of physical distance. That was a code. I'm just checking there are no questions at this point. Otherwise we can just continue. Lucas, you don't have
I don't see any questions apart from you here. No.
Yeah. So we can go to the next topic, and I know Lucas, I think you are not. Maybe you have been, but both me and Federico have been database consultants. And
I worked at several nines for a bit, yeah. So I not as a database consultant, but in marketing. So
so you know, like when you work as a database consultant, there is like a majority of cases is a really simple thing that you do. Customer has a slow query, and you go there and look at it, and use some kind of like explain or query analyzer, and always the fix is you add one index and then you go home, right? And like I used to say that in 50% of the cases this is what you do, and then before SSDs were invented, the joke was that then for the other 50% you can tell them to buy more RAM, and then like whatever problem they had, it will get faster. And this is all you need to know to be a good database consultant. And now from this background, it's interesting that what if databases didn't have indexes, like, or what if databases indexed everything automatically for you, and this work would go away? I don't know if we have SSDs, so you don't like we have SSDs and RAM in sufficient amount, and you don't need to think about indexes. I don't know if you need database consultants anymore, and we would need to find something else to do. So first question is in this what columnar databases do? So kind of, but that's like for a very specific use case. So columnar databases mostly, I would say they are very, it's very cool what they're able to do, but in a way it's just making table scans or column scans very fast, so that you don't benefit from indexes. But but there are like many other queries then that wouldn't make sense or don't perform well on a columnar database. So there are two databases that have done this, and unfortunately the rock set that was well known no longer exists because it was bought by OpenAI and they use it internally. And then they told all the other customers just to migrate away and find something else. In the Rockset's case, of course, they used RocksDB, so it was an LSM database, just like Cassandra, by the way, that we just talked about. And so their idea was that, okay, like RocksDB is efficient for writes, so if also the secondary indexes are in this kind of LSM structure, maybe they are cheaper to write. And I remember the blog post that is no longer available. At least I couldn't find it. I think the overhead was like 4x or so. The disk overhead is 3x, which makes sense because in Rockset, they didn't just index every column, but they actually indexed every column 3 times because they did separately, like a B3 index and a columnar index and then a search index. So like the disk overhead being 3x is kind of expected. And the CPU 4x, of course, this was a cloud service, so it was invisible to customers anyway. But I would say it's manageable, and in any case, the fact that this is possible at all, like we are talking about maybe tens of columns that get indexed, is quite amazing. And another database that actually exists and you can use it. It's not very well known, unfortunately, but I worked with them last year. Is CrateDB, a European or Austrian team originally, and CrateDB is actually, it's kind of like a fork or borrow the internals of Elastic, which is mostly, so essentially it's like Lucene indexes or Lucene search engine with SQL database as a front end. And I remember when Elastic was becoming popular, I think many people liked using Elastic a lot and were thinking that, oh, like I will just use this as my main database. And then like people who, like the creators of Elastic, were busy telling her that no, like you cannot use it as a database because it's not a database and we are not trying to be a database. But CrateDB essentially is this, what if Elastic was a database? And here also, I would say the most recent version that I saw when I was still there, the overhead is really small, like it's less than 2x. So okay, so now it's like the wrong way, but like 50% or so 0.5x or 1.5x, depending on which way you think about it. But yeah, so and this was for a test indexing 10 columns, for example. And what happens there is, so of course if you write the same data into a MongoDB or a MySQL database, then many queries return in milliseconds. And what happens with CrateDB is that you rarely, unless it's really a key value query, but for this like Lucene based index, you don't really get response times that are 1 or even a few milliseconds, but it's usually like tens or this 200 milliseconds, which is a very typical example that I took here. But the cool thing is that you really can do this for every query, or if it's like a really complex query in time series benchmark, for example, the last queries get more complex, then maybe it's like some 4 seconds or 10 seconds. But on many competitors, those queries don't complete ever. And you get this for free, like you just insert data, you don't have to think about indexes. I thought it was pretty amazing, and it's like a completely different user experience. So I hope this idea will spread, or that CrateDB becomes popular, or both maybe. And I think with both of these, so one was based on LSM, CrateDB is based on Lucene, but especially Lucene index structures. The lesson here is that they are, Lucene has some very interesting and efficient index structures worth paying attention to. An interesting thing here is that they don't sort the data on writes, and it took me many months working with CrateDB before I realized this, or somebody pointed out to me that the reason things are sorted when you query. So this is also one reason why you then see often these kind of hundreds of milliseconds or a few seconds latency. But in a distributed cluster, that actually goes pretty well. And the other thing is that many analytical queries, you don't benefit from a sorted index, because like you would in any case do some group by or something. So the output that you then want to return in sorted fashion is completely different than the data stored on disk. So those kind of observations, I never would have thought this would have been possible, but luckily we have these products that prove that it is, and to me this is one of the most revolutionary things that I expect to see happening in the database industry. On a completely different level, of course, quantum computers. Should we just jump into that one?
We still have time, so if you want to, you can, yes.
Yeah. So again, good. I'm a big fan of the Nobel Prizes, and I always watch when they do the toasts in Stockholm at the dinner. So I'm looking forward to this one, and I'm a bit jealous that actually a former colleague from DataStax now has his own startup in the quantum computing space, and he actually works together with John Martinez, who now won a Nobel Prize, and they celebrated it, and then they went back to work. So greetings to Alan if you ever watched this. So I just want to point out that I actually have an education in physics, and somehow managed to pass. So the lowest grade here, number 2, is from the course that introduces quantum physics and the Schrödinger equation. And I honestly don't remember if I ever managed to solve that equation, but maybe out of pity, I passed this course anyway. So this is just to say, like, all this database talk, I'm completely unqualified, and it's kind of like just learning on the job that I had to do. But physics, in theory, I have some academic studies behind it. I have friends who work at IQM, for example, in Finland, but there is a reason why they work on quantum computers and I don't. So at least I'm close. I did this announcement on April 1st, so I just want to kind of confirm that it's not true. I don't have a quantum computer in the backyard here in the home office. But it was like, because many people know that I studied this. There were many people who actually weren't sure whether this is a April Fool's joke or not. And to be fair, if somebody wanted to buy performance services like performance testing for a quantum computer, I probably would say yes. Doesn't mean that I would know what I'm doing, but it would be an interesting project. But for this talk, of course, we have to start talking about, and like maybe somebody will get inspired to start a GitHub project. What would it look like to do a quantum a database for quantum computers? Like, does it make sense? Is there some benefit? And of course, to answer this question, we have to start with asking like, how do these quantum computers then actually work, and what algorithms might be relevant for databases. So quantum computers have these qubits, and the typical mainstream understanding is just like this example with the Schrödinger's cat that's in a box, is that the cat is at the same time both sleeping and awake. So this is kind of like a superposition where two realities are true at the same time, except until you open the box and make an observation of the cat. It's always one or the other, and that's where this superposition collapses. And then when we do quantum computers, this is essentially just like, now today you can buy like 50 qubit computer, for example. So this is essentially just like having 50 cats in this superposition, and then when you open the box, they are all alive or sleeping or dead. And somehow magically, if you use then this phenomena to solve the traveling salesman problem, for example, the cats somehow magically collapse into the shortest path by some kind of cat instinct, and that's not actually how it works. And what happens instead, and this is how qubits are described. So the right way to think about this is that the qubit actually is a 2 or 3-dimensional vector. So one of the directions is like the 1 and 0 that we observe. So the cat being either awake or asleep, and then the vector also is pointing in some other direction, but this we can never observe, and because and this is why quantum these quantum phenomena, or qubits in this case, appear to be somehow like random, is only because we don't actually, like, they are actually in a well-defined state, we just can never see it, and then every time we make some measurement, we always get just like the 1 or the 0, and that's why it appears somewhat like arbitrary to us. So now when you use quantum computers, then these qubits have been engineered so that you can manipulate them with these kind of basic operations, and these are the quantum equivalent to Boolean operations that we have in classical computers. So basically what you do is all quantum algorithms do is that they combine these NOT and Hadamard gates, and then a control NOT, which is a operation, like conditional operation, using 2 qubits. So that's how we can kind of read or figure out what state the qubit was in. And so indirectly then we can kind of control and figure out how this vector was pointing, so that it appears less random. Often also the quantum algorithms, of course, are statistical. So you repeat them enough times, and that's kind of what you would do if it was a random phenomena, but it's not. But it looks very similar. Even a notation with these brackets looks similar that you would have in probability math as well. So just want to advertise a paper. So basically, Andre Berthiaume in the 90s has written this kind of paper where he defines an abstract machine that is the quantum equivalent of a Turing machine, and all quantum algorithms then are built on this, and the goal for IBM or IQM or Google, who build physical quantum computers, is to somehow out of physical qubits build a computer that can do these operations defined in these papers. And the funny thing in these algorithms is that there is this concept of an oracle in many of these algorithms. So, for example, if we go to an algorithm called Grover's search, it's defined such that you have a space of strings which are encoded in bits. So if you buy, for example, now a quantum computer with 50 qubits, then you could run this algorithm on at most 50-bit strings. And and one part of the algorithm is that we have this function which is called oracle, which will tell you whether like we are searching for a specific string. So this oracle function will tell you whether some bit string is a match or not. And of course, this kind of abstracts away most of the actual work, which could be like a regular expression, or it could be some just like bitwise AND, of course, in the simplest case. Or in this case, actually, the oracle would be bitwise AND. But all of these quantum algorithms actually sidestep the problem of how do I get my strings, which in this case could be like a database. How do I actually get them into these qubits, and how do I execute this oracle function? This is like completely sidestepped in the algorithms. The algorithms just say that like once you figure out that part and you have a function that can tell me whether there is a match or not, then what the algorithm does is like iterate over, in this case, an unsorted set of strings. So this is not quite a database. This is like maybe this is a full table scan, so an unindexed database, or maybe this is actually like a MapReduce version for quantum computers. Anyway, what is remarkable is that if you have n strings and you run this algorithm in a quantum computer, and you somehow figured out how to get your data into the quantum registers, so some kind of memory, which is also in the quantum domain, then the time to find the correct string in this unsorted set is actually the square root of n, which is mind-boggling, because like how, if you think about classical computer, then of course if you have n strings and there is no sorting or indexing going on, then probably you have to look at each string, and I mean that's what you have to do in classical computers. And somehow these quantum effects actually kind of can sense even the strings you didn't like before you tested them. So this is similar similar magic to this like very basic test where you have light that passes through two gaps in a wall or something. So for a normal person, this is like impossible to understand, but this is how it works. So what did we learn here? So the quantum computer didn't solve this in 0 times with some magic cats who just like find immediately the right string. So it's still like consuming time, but it is more efficient than a classical computer. And why is it square root of n? So one explanation I heard is that it has to do with this 2-dimensional or 3-dimensional property. So in fact, if you think about it, we always say that the qubit can be in 4 states instead of 2. And now if you had a classical computer which somehow, like maybe because you had 2 CPUs or some, like somehow magically you were allowed to always take 2 bits at a time for this kind of matching algorithm, then actually n also becomes like square root of n. So that's basically what's going on, or at least how I understand it. And so here we have an algorithm that for a database without indexes. So I think this is Hadoop probably. A quantum computer would, in theory, be faster. The only gotcha here is which is the algorithm bypasses is that you somehow need to get your database into these quantum registers that are next to the qubits, and they must be isolated. So like there is no classical observation or like no interaction with the outside physical world while this is executing. So from here there is a cool page which lists all the quantum algorithms, so you don't have to like read every paper, or you can look up the algorithms here and then read a paper maybe if you are interested. So similar kind of algorithm exists for wildcard search. Interestingly, it's not just a wildcard version of Grover's algorithm. It's a different algorithm, but it also happens to be square root of n. Then there is something called quantum amplitude estimation, which actually as an algorithm is very similar to the search, but instead of searching for one thing, this could be used to like compute the sum or count, or so you could implement actually all the aggregation functions with this algorithm. And I think here the word estimating has to be understood such that the estimate is actually the correct result. Like once you run it once you iterate enough times, then the estimate is actually like 100% probability true. At least that's how I read it, but I might be wrong. And then of course we have traveling salesman problems, any kind of combinatorial problem, which if you brute force it in classical algorithm is this n exclamation mark? What is it called in English? I forgot. And even even if you use this Heldt-Karp algorithm, it's like exponential time. So in quantum, this is interesting number. So it's also exponential, but instead of 2 to the power of n, it's like 1.7 to something to the power of n. And when I first saw this, I thought that, okay, so isn't it essentially the same? But in practice, if you start counting with like n 10 or 100 or something like that, it is a pretty huge difference. So and where could we use this in a database? Of course, already in query optimization, I didn't know this when I was younger, but in query optimization, it's a hard problem if you have like 10 or 15 joins in a SQL query. The number of ways you could choose to start executing these joins is exactly this problem, and it turns out that even just like so when a query optimizer, even if you have like a good cost-based optimizer and you have good statistics of your tables, the query optimizer cannot afford to actually like check all the different combinations of join ordering that you could have, because just like running that would then take too much time, and it's more efficient to just like do some kind of fast search and then start actually executing the query, which is where you start getting results. So yeah, this could speed up that, but again, it's not like a magical speed up. But I thought I said that there is something connecting.
I'm sorry, Henrik. We
Yes.
are running out of time. We have
Yes, so we are at the end, luckily.
yes,
And
we
like,
have 3-4
yeah,
minutes before the next speaker. So
yeah,
if you could
that's
wrap up.
perfectly fine. Yeah, so what I was saying, that the thing now here at the end, which connects this quantum topic to the previous topic, is if you had a database where every column is indexed, then you have more choices, and this combinatorial problem for the query optimizer actually gets worse, even though it's a better database to have all those indexes. So maybe this could be a solution, and to use a quantum computer to choose the optimal execution plan for a query. And then last here on the right hand side, there are a couple of papers where somebody has already asked this question, that all these algorithms are great, but how do you then actually get the data into this Oracle function? And if all of this was very theoretical, I just want to point out that you can actually use quantum computers, several of them, in AWS, and it just so happens I see it's very popular. I think they got a lot of registrations. IQM is organizing a 2-day course next week if you want to learn quantum programming. I will probably not have time to do that, but if you do, and you start a project on GitHub to write a database for quantum computers, then please let me know.
Thank you, Henrik. I see that we don't have any questions in the Q&A. If anyone
Yeah.
has any questions, please ask them as soon as possible, because in a couple of minutes we have the next session.
Yeah.
If
I kind of used the time also. I didn't anticipate that there weren't questions coming.
Yeah, I mean, I don't see any questions that are coming your way, so
Yeah.
unfortunately we have to wrap up. Thank you for your time, and I hope you
Thanks for inviting me.
enjoyed the event. Yeah, thank you. It was a nice talk.
Yeah. All right. Bye.
Thank you. We have now in this track we'll have Greg Chemnitz in a couple of minutes, so I'm gonna stop the stream.